Many of the things that we care about in probability are numbers, numerical things, random numbers. So if we think about rolling a die, for example, we can say, hey, what if I roll two die and I add the results together? That's a new number. It's a number that's been randomly generated in some way. Or if I flip a coin some number of times and I count the number of heads, that's a random number that I've generated in some way. Random numbers that are more practical in many cases might be things like, hey, if I generate some data and run an algorithm on it, how long might I expect that algorithm to run? The runtime of that algorithm might be a random number that we would care about understanding and quantifying. So all of this brings us to the topic of random variables. So random variables you can think of as random numbers in probability experiments. A little more formally, if I have a sample space that I'll call S, a random variable in the formal definition, and we almost never work with them this way in applications, but it's good to know the formal definition. What it is, a random variable is a function that I'll call big X here. This function goes from the sample space to, we'll just say real numbers, but it could be any set of numbers here. So what it does is it maps an outcome to a number. So you can think of it as a measurement. If my outcome is I roll a die, or maybe I roll two die, then the measurement might be adding the two numbers together. Or if my outcome is a sequence of coin flips, my measurement might be the number of heads that I get. So we can think of this random variable x. It's a rule that assigns some real number x of a here. So a is an outcome. So I take some outcome in my sample space, I assign it a number, the number I think of as my measurement associated with that outcome, and that is my random variable. So here's one example to get us started. Suppose that I flip two coins, and I'm going to measure the number of heads. So x is going to be the number of heads that I obtain when I flip two coins. So here we are. What I'm going to do is I'm going to enumerate the sample space. So here's my set of possible outcomes. When I flip two coins, I could get heads, heads. I could get heads, tails. I could get tails, heads, or I could get tails, tails. And then the value of my random variable x here, okay, so x is the number of heads. So in my first outcome, I had 2. In my second outcome, 1. Third outcome, 1. And final outcome, 0. So I don't know what the probabilities are yet because I didn't say whether the coins are independent or what their probabilities of heads were. I just said I'm flipping two coins. But I don't need to know that in order to be able to measure the random variable x associated with each outcome a. Here's another example we can do. So let y, different random variable, be the largest of 3 rolls of a 6-sided die. So I'm going to roll 3 die. I am going to look at the largest of those rolls, and that is going to be the value of my random variable. So let's look at a few examples here. So one way my 3 rolls could come up, they could all come up 1. In that case, the largest value is 1, and so my random variable would have value 1. On the other hand, maybe one of them comes up 2. That's the largest, so my random variable would have that value. And I could just enumerate all the elements of my sample space. There's too many for us to do together here. But here's a few more. If I get a 5 and 2 6s, I would get a 6. And then finally, kind of the last outcome here, they could all be 6. And then I'd get a 6 as well. So in all of these cases, I do something random. I flip a coin, I roll a die, I generate some data. And then once I've done that random thing, I do a measurement. I count something or measure something in order to obtain a number. In this class, we'll usually be focused on integers. Integers. And that number in each outcome defines a random variable. The random variable technically is the rule for assigning that number to the outcome. So informally, we often think of random variables as random numbers. We say, oh, here's my possible values of x here. I look at all the outcomes. These are random, and so the measurement itself is random, and so I'm generating a random number. This is a useful way to think about it, and it's the way that we're going to think about it in much of the rest of our discussion of random variables. Many times in probability problems involving random variables, we have to think about multiple random variables, and we're going to measure two things and then combine those measurements in some way. So let's talk about how we can do this. We can define multiple random variables on the same sample space S. So we're going to look at measurements that we can take on the same set of outcomes. If we define our measurements on different sets of outcomes, then we are not going to have something that's intrinsically meaningful. And so we're going to focus on measurements that we can take on the same sample space S. So the thing is, once we do measurements, maybe we'll do two measurements, then we'll get two numbers. And once we have those two numbers, we can do any kind of combinations of those numbers we want. We can do arithmetic, for example. We can add or subtract or multiply or divide them. Technically, what we're talking about here is if I take two measurements, random variables, x and y, defined in the same sample space, then technically the sum, x plus y, it's also a random variable, which means it's a function that I call x plus y from the sample space to R. And the way we evaluate this function is that we say, hey, the result of x plus y on outcome A, that's equal to the sum of measuring x on A and then measuring y on A for any outcome A. So this is pretty abstract, so let's do an example to make this a little concrete, where we combine two things that we've measured, two random variables. Suppose that we flip 5 coins, then let x, our first measurement, be the length of the longest consecutive string of heads, and then let y be the total number of tails. So I'm going to get a sequence of 5 heads or tails, 5 coin flips, and I'm going to measure these two things, and then I'm going to be able to combine them in whatever way that I want to. So let's take a look here. I'm going to make a little table. So I'm going to define some outcomes, and I'm not going to enumerate all of them, but we can look at a few. So here's one, which is the all heads outcome. Here's another in which I have heads, tails, heads, tails, heads. And here's one more in which I have heads, 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 tails, tails. And then there's lots more outcomes, but we don't have to spend all our time looking at those. So what I'm going to do is I'm going to define my two measurements, and then I'm going to look at their sum as well. So here, x is the number of consecutive heads, so the length of the longest consecutive string of heads. Here I have 5 consecutive heads. That's clearly the longest one. So x is equal to 5. Next, I actually don't have any strings of consecutive heads except for each individual heads themselves. So that's 1 in this case. And then in our last one, I have 3. On the other hand, if I measure 5, the total number, or y, the total number of tails, I'm going to have 0 tails in my first outcome, 2 in my second, and 2 in my third. And of course, we're going to have an x and a y for each of the other outcomes as well. And so if I want to combine these in some way, I can add them together. 5, 3, and 5. If I wanted to, I could do even more things. I can multiply, for example, so I would get 0, 2, and 6. So once I have these measurements defined on the same sample space, I'm allowed to combine them in arithmetic ways using any kind of arithmetic operation I want. And this is going to be helpful for us in various cases down the line where we have a random variable that we might want to study, and we might be able to express it in terms of other random variables, which we then combine to get the thing that we actually care about. So just a reminder here, this is pretty important. I was able to do these kinds of combinations because x and y are defined on the same sample space. So just a little reminder here. I can meaningfully add or more generally combine random variables when they are defined on the same sample space. If they're not defined on the same sample space, then I am not able to do this directly. So technical point, keep your sample spaces straight. If you want to combine random variables like these, you have to define them on the same set of outcomes. And once you've done that, you can do arithmetic with random variables to generate new random numbers from old ones.